Hello everyone, welcome back to Quick Coding Bites. Today we'll be taking a look at another topic that is tested on the ACSL contest, assembly language programming. Assembly language is the language of computers. Programs written in high-level languages are traditionally converted by compilers into assembly language, which is turned into machine language programs, sequences of ones and zeros by an assembler. It is important for programmers to learn assembly language because it provides programmers with a better understanding of how compilers and their constraints are. Further, sometimes programmers find themselves needing to program directly in assembly language in order to meet some constraints in execution, speed, or space. Assembly language's basic concept is a bit different than most programming languages. Assembly language, for most part, runs sequential with only a few commands that cause branching. An assembly language program is terminated when the end command is encountered. In assembly language, there exists what is essentially a working memory block or a working space known as an accumulator, which stores the result of operations. Assembly language programming is centered around the accumulator, and every operation is run through the accumulator. Each assembly language command has 2 or 3 parts. It looks like the following: label, opcode, and lock. A label is used for branching, which we'll be looking at later, and is the optional part. Opcodes are reserved keywords in assembly which perform specific actions. The lock is a reference of a memory block or actual physical, literal data. Now, let's take a look at the opcodes or commands that exist in assembly. So the first opcode I would like to talk about is DC. So what DC does is it takes the value of the memory word defined by label and sets it to a specific constant. So label field is mandatory for this opcode, and the accumulator is not modified. So an example of this, I'll show you it right now, would be something like ADC7. So what this essentially does is it sets A to equal to 7. So the memory location A to equal to 7. Then we can go in order. So load takes the contents of lock and places it in the accumulator, and the contents of lock are unchanged. So I can do load A. So what that would do is it would put the contents of A, in this case 7, into the accumulator. Store takes the contents of the accumulator and places it in the lock. And in this, accumulator is also unchanged. So in this case, if I did store A, then whatever the accumulator currently had inside it would be stored into A. The next one we'll look at are add, subtract, multiply. So what this is these are just arithmetic operators. So the contents of lock are added to the content of accumulator, subtracted, multiplied, divide. So the sum is stored in the accumulator. So sum, difference, product, signed, or sum, difference, product, and the signed integer part of the quotient, everything is stored in the accumulator. And the lock is unchanged. So this may seem a lot wordy at times, but essentially what this is let's set it back to load A, and we can do add 3, for example, and then load, or you know what, instead of that, let's do this: BDC8, load A, and let's add B and store in A. So I'm just combining a couple of the opcodes we have. So in this case, so we load A into the accumulator. So the accumulator has 7. Then we add B to it. And when we add B to it, it will take a 7 and add A, 8. So that turns into 15. And B is not changed. And A is actually still not changed. the accumulator now has 15. And we need to store into A, and that A is now set to 15. So that's the basic premise of add, subtract, multiply, divide. We'll look at another example later. BG, BE, BL, BU are branching. So this is the if-else statements, but they're constant. So BG would branch to the instruction labeled with lock if accumulator is greater than 0. BE would branch if the accumulator is 0. BL would branch if the accumulator is less than 0. And BU just branches without any condition. So what does that really mean? So I'll show you an example of this at the end. When we do an example, read a signed integer into lock. So what this does is basically human input. You put in a number and it puts it into what the lock represents. Print prints the contents of the lock. We talked about DC. And end, as I mentioned earlier, is the end of the program and it terminates the program. And the lock field in this case must be ignored and empty. Now that we know the basis of assembly language, we can now take a look at a sample assembly language program. If you don't understand how the accumulator works in a program until now, this example will help make that clear. So let's start. So right before we start, I'm going to actually make a table. And before I do that, you can see that there's going to be 3 variables here, as the DC declares a variable, and actually 4 because of temp. And I told you that the accumulator is also a memory block, except it doesn't really have a special name, it's just a working place. So we're going to have 5 different memory blocks, so 5 by 2. Let's move this here over to the side. Let's get this bigger, and then I want 20. And so this is temp, this is A, B, C, and accumulator. And now let's set the initial values. So accumulator initially doesn't have any value, so I'm just gonna leave it as this. And we can see, so temp DC 0, so temp starts at 0. A is 8, B is -2, and C is 3. Now let's start. So load B. So what happens now? Before we do that, I'm gonna go line by line because I think that makes more sense. So load B. So we're gonna load the B into the accumulator. So accumulator now is -2. Then we're gonna multiply by C. So -2 times 3 is -6, and so we're going to keep that in the accumulator. We're going to add A to it, so A is 8, so 8, or -6 plus 8 is 2. We're going to divide by B, so 2 divided by -2 is actually -1. Subtract A, so -1 minus 8 is -9. And we're going to store it into temp. So now temp is -9. And so the question asks, what's the final value of temp? So the final value of temp is, in fact, -9. So that's the basis of how assembly language works. You create these variables, you do these arithmetic operators, whose answer is stored in the accumulator until you decide to store it somewhere else. Let's look at this next problem. So this problem reads, if the following program has an input value of n, what is the final value of x when it's computed? Express x as an algebraic expression in terms of n. Before we start going through the problem, let's look for some clues which can help us understand how to solve it. We see that there's branch instructions, BU and BE. Therefore, there will be some looping involved. We also see that there's a sub command. That means we're looking for something to get decremented. With this in mind, let's start working on the problem. We see that there's x here, which we know is n, and we also see that we're storing it in a variable called a. So I'm going to create a table, and let's make it a 2 by 2. we have x and we have a. So first, and actually I forgot about creating another for the accumulator. So let's go ahead and do that. Accumulator. So at start, there's no value in there. So we're read x, so we know x is n. We're going to load x into the accumulator. So now accumulator is n. We're going to subtract 1 from the accumulator. So accumulator is now n minus 1. And be done. Well, we know that it will only be done when it's 0. Well, n minus 1, the loop or this program will leave when the accumulator, so when n minus 1 is equal to 0. But now let's understand what happens with everything else. So what do we do next? We store it in a. So a actually is n minus 1 now. We're going to multiply by x. So what was x originally? N. So what are we doing? We're multiplying n minus 1 times n. And then we're going to store that in x. So now x has this. And then we're going to load a again. So now in the accumulator we have n minus 1. And we're going to branch back up to top. And then this repeats. So you subtract 1, so now accumulator is n minus 2. And we store n minus 2 in a. We multiply by x. So technically now we would be doing this, where it's n times n minus 1 times n minus 2. We're going to store this result in x. And then we're going to load a. So a is now n minus 2. And then this cycle repeats. Now you'll start to see a pattern. So this will terminate when a, so when n minus 1 or n minus whatever is equal to 0. Well, this looks like a popular arithmetic operation. It's the factorial. So we can express x as an algebraic expression in terms of n because we know this will loop a times whatever n is. So a would be n minus 1, so it's a times. So this, in fact, the answer to this problem would be x is equal to n factorial. So as we saw in this problem, it's not always about just going cycle by cycle to determine what the answer is. You have to understand what the core of the program is and what the program is actually trying to do in order to solve the problem. So just cycling through it won't ever get you the right answer in this case. You have to understand what the input is and how the output is related to the input in order to determine the answer. As with most other problems, this requires a lot of practice, and once you have a lot of practice, you should be good to go. So stay tuned for more videos, and thank you for watching.